Picture a coral reef. You're probably imagining this perfectly serene, beautifully crowded, brightly colored underwater paradise, right? It looks like the ultimate cooperative ecosystem, everything just kind of harmoniously growing together. Well, scratch that. Beneath that super tranquil surface is actually a hidden, highly tactical, and quite literally toxic underwater battlefield. So in today's explainer, we're diving straight into the invisible war raging right now on the coral reef. Here is our tactical briefing for today. We're going to cover 1. The invisible reef war. 2. Defining allelopathy. 3. The stealthy symptoms. 4. Rethinking reef frustration. And finally, 5. Forecasting the future. All right, let's jump right into Section 1, The Invisible Reef War. Subtitle, Shattering the Illusion of Peace. I have to ask you, are coral reefs really as peaceful as they look? We tend to view corals almost like, underwater rocks or maybe gentle plants. They just seem so static and completely harmless. I mean, they don't have claws, they don't have teeth, they aren't chasing each other around the ocean. It's incredibly easy to just assume they are passive background characters in their ecosystem, but we really need to question that assumption. Okay, let's dive into this. The truth? Corals are actually fiercely aggressive territorial combatants. Think about it. Reefs are insanely crowded ecosystems. Down there, real estate is absolutely everything. So to secure vital space and the limited resources available, corals actually wage an invisible chemical warfare against their neighbors. They are definitely not just passively sitting there. They are actively fighting for their right to exist and expand. Moving to Section 2, Defining Allelopathy. Subtitle, The Chemical Weapons. So how exactly do they fight without, actually moving? The scientific mechanism driving this hidden aggression is a process called allelopathy. Allelopathy is defined as the release of chemicals by an organism to inhibit the survival, settlement, or growth of potential rivals nearby. And the absolutely crucial part to remember here is without requiring direct contact. A coral doesn't even need to be touching its neighbor to launch a strike. It simply releases these toxic compounds straight into the surrounding water to neutralize the competition. If we compare the two main strategies of coral competition, the contrast is pretty stark. On the left, you've got overt dominance. This is the stuff we can easily see. Rapid, space-claiming growth where one coral physically overgrows and shades out another one. But then on the right, we have allelopathy. This is that stealthy, invisible chemical release that completely alters the local community structure. And the crazy part, researchers point out it's not an either-or situation. On the reef, both of these strategies are often operating at the exact same time. You've got corals physically expanding while simultaneously blanketing the area in chemical suppressants. It makes predicting the outcome of these turf wars incredibly difficult. And who exactly is getting hit by these chemical weapons? Well, the collateral damage is huge. The targets of these chemical strikes include competing algae that might try to smother the coral, other adult invertebrates, and, perhaps most crucially, larval stages. That means literally baby organisms floating in the water just trying to settle and find a home are being actively repelled or killed off by the chemicals released by adult corals. It is a brutal defense mechanism. But the effectiveness of this chemical warfare isn't just a constant. It's super complex and fluctuates based on a few key variables. Step 1 is water flow. A strong current might just wash the chemicals right away, whereas stagnant water can dangerously concentrate them. Step 2 is distance. Obviously, the further away a rival is, the weaker the chemical strike. And step 3 is the coral's own physiological state. A healthy, stress-free coral might pump out way more chemicals than a sick one. Because of these three compounding layers, the intensity of these effects can literally change day to day on the exact same reef. Section 3. The stealthy symptoms. Subtitle, The Hidden Casualties. So, the crucial point here is perfectly captured in this quote. Damage doesn't always look like immediate die-off. If you're out there expecting to see sudden, dramatic, scorched earth zones of dead, bleached corals around an aggressive neighbor, you are looking for the wrong thing. This warfare isn't explosive. It's a slow, highly stealthy poisoning. Instead of instant death, the stealthy symptoms of allelopathy show up in way more insidious ways. A coral getting hit by chemical warfare might just show slowed growth or heavily reduced reproductive success. We also see impaired settlement, where new corals just can't take hold in the area. Over time, this leads to massive shifts in which species are actually able to establish themselves. And because these changes are so gradual, short-term observations by scientists or divers might completely miss the damage. The reef looks the exact same today as it did yesterday, but the underlying community is actively being reshaped by these invisible chemicals. Section 4. Rethinking Reef Restoration. Subtitle, High-Stakes Interventions.
This invisible reshaping of the community has massive real-world implications, especially for how we interact with the ocean. Human intervention to save dying reefs is a huge, high-stakes global effort. And the traditional approach to restoration projects has been pretty straightforward. Scientists take healthy coral fragments and transplant them into defined areas that need rebuilding. The basic expectation has always been that, hey, once you plant them, you'll see a stable, predictable progression toward a healthy, thriving community.
But building on what we've just learned, if chemical warfare is a primary driver of who dominates locally, simply dropping random corals next to each other is a literal recipe for disaster. Restoration teams are realizing they have a whole new set of crucial variables to deal with. It's a real game changer. It's no longer just about picking a healthy coral, it's about the choice of the specific donor species and heavily weighing who the neighboring species are going to be. If you transplant a fragment right next to a chemically aggressive neighbor, your carefully placed transplant might just fail to survive. So exact placement patterns on the seafloor are now literally a matter of life and death, dictated entirely by these invisible chemical borders. This dynamic is also absolutely critical for natural recovery. Think about after a major disturbance, like a violent storm, a severe heat wave, or a pollution event. The reef is heavily damaged, right? Some corals dry off, which means the competitive pressure suddenly changes. In that chaotic aftermath, allelopathy steps in as a major factor. The chemical interactions happening right there in the rubble help determine which species get to rebound first and establish dominance, and which ones stay suppressed and pushed out of the new ecosystem. It's like an invisible hand guiding the reef's recovery.
Section 5. Forecasting the Future. Subtitle: Predicting the Winners and Losers.
To actually manage all of this, scientists are diving into some intense laboratory and field measurements. Their current goals are highly specific. First up, they need to identify the exact chemical compounds involved in this warfare. Second, they have to quantify exactly how far these compounds spread in real flowing ocean conditions, not just in a pristine lab tank. And third, they have to separate these chemical effects from everything else corals fight over, like competition for light, nutrients, and physical substrate. It's literally like trying to solve a giant, invisible puzzle. And this brilliantly illustrates exactly where marine biology is heading today. The ultimate goal isn't just to sit back and observe. It's about translating this intricate chemical ecology into reliable forecasting tools. We are moving away from just describing who outcompetes whom after the fact, and moving towards actively predicting how entire reef systems will reorganize themselves in the face of ongoing climate stress and human impacts.
So I want to leave you with this final thought. As our climate changes, the stress on these incredible ecosystems is only going to intensify. As we build models to predict their survival, how will our understanding of this invisible, microscopic war dictate the future of human intervention in the oceans? Can we play peacekeeper, or must we carefully manage the battlefield? It's a massive challenge, for sure. But by understanding the secret chemical language of corals, we are one step closer to actually saving them. Thanks so much for joining me for this explainer. Keep questioning what you see and keep learning.